Hello, everyone. Welcome to lecture number 2 of EEPS 1810, Physics of Planetary Evolution. And based on your reading for today's lecture, you have some sense of how solar systems, our solar system, and other star systems form. And so what we're going to focus on for today's lecture is supplementals to that reading, namely diving a bit into the Big Bang and the formation of the universe, as well as the formation of the solar system and some of the theories surrounding how the early solar system evolved and how those key evolutionary differences might explain aspects of our solar system that haven't been explained otherwise. Okay, so before we dive in, I think it's helpful to get some understanding of general definitions. So let's first start with a planet. A planet generally orbits a star. Our star is known as sun for our solar system, and it tends to be rounded by its own gravity. And there is no thermonuclear fusion that goes on in planets. If there were thermonuclear fusion that went on, we would generally refer to that as a star. Um, as some of you might be wondering, well, under this definition, it seems like Pluto might fit that general definition. And that would be true. Uh, for this general definition, I'm not getting into the technical aspects of why Pluto isn't a planet or some of the more precise wording of a planet. But when we think about Pluto or a planet in general, a planet is considered to be a planet if not only it orbits a star, but it's generally cleared its orbit. So it's the most massive object sort of along that orbit. That's one way of thinking about it. And in the case of Pluto, its moon is a big part of sort of the mass of that system. And so it's not generally considered that Pluto has cleared its orbit because its moon is so large. Now, if that moon went away, or if that moon merged with Pluto, Pluto would then be considered a planet. All right. But we won't generally get into that level of definition for this class. Okay, secondly, star. What is a star? A massive luminous ball of plasma that shines due to thermonuclear fusion. This definition will become very apparent as we start to dive into the evolution of our solar system as well as the universe, because we'll use other words to define what will eventually become a star. So until thermonuclear fusion in uh, a star is has started, we don't generally consider that object a star. And then a galaxy is a system of stars. And so our galaxy, as many of you may know, is the Milky Way. Okay, so let's move on. All right, so this is the abundance of elements in the universe normalized to silicon. All right. And on the y-axis, we have that log normalization. And on the x-axis, we have the atomic numbers of the elements. And there are a few things that should pique your interest here. So one is we, to first order, see a trend where there is decreasing abundance with increasing atomic number, right? Um, just right now, I could probably, excuse me, we could probably also notice that hydrogen and helium are the most abundant. There tends to be a peak for some reason at around iron, seems to be higher than the rest, and then it declines afterwards. And we also see this low right here around lithium, boron, and beryllium. Okay. Um, but altogether, there are really six major observations. So the hydrogen and helium are most abundant. Again, the elemental abundances drop with increasing atomic number. You might also notice that the even number elements are more abundant than the odd number elements. Lithium, beryllium, and boron are anomalously rare or have very low abundance comparatively. Iron, as I noted, is anomalously abundant. And that these elements, as well as those with atomic numbers greater than 83, also seem to be extremely scarce or non existent. All right. And when we think about the formation of our universe, this is one of the main things that needs to be explained. All right. And the Big Bang Theory does this. No, 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 not that Big Bang Theory. No, this Big Bang Theory. Um, and so some of you might be familiar with elements of the Big Bang Theory, but the general idea is around 14 billion years ago, uh, there was a Big Bang. And that Big Bang resulted in debris, if you will, and that debris was sort of the matter that composes our universe. Um, and that debris forms our stars and our planets. Okay, so the Big Bang. Where did the notion of this Big Bang start? And I would say it probably started with one of the most famous papers that have existed regarding the formation and evolution of our universe, and that came from Hubble in 1929. And so in 1929, Hubble did a series of observations, and those observations show that a galaxy's distance is directly proportional to its redshift, which is a proxy for velocity. And by redshift, if you recall the Doppler effect, right? And this is, we probably experience this with ambulance or police when the sirens are moving closer to us or moving farther away from us. We hear a shift in their frequencies, right? And that's true of objects when they move farther away from you, their frequency will be shifted in one way, or when they move closer to you, their frequency will be shifted another way. Namely, if an object is moving away from you, the frequency will be decreased, and if they're moving closer to you, the frequency will be increased. All right, and this is this allows to determine, or at least get a proxy for velocities of galaxies that you might observe. And so one of the things that Hubble did is he took data that was measured from another scientist, whose name I do not recall at this point, and he plotted the galaxies, which are shown as red arrows here, um, with respect to distance and the redshift, again, that proxy for velocity. And what was noticed, and I should say the distance here is in megaparsecs, and 1 parsec is equal to 3 times 10 to the 13th uh, kilometers. And I'll just see if I can go ahead and throw that here. And we'll just make that note. All right. And what you see is for a good portion of this data, um, it falls along a straight line. And the Virgo cluster here, which is shown in this big circle, and so there's additional data there. We're not going to get into that, but that wasn't shown in his original data set. This is an updated data set. And just for illustration, this is what his original data set looked like. And let's see if we can make that look a little bit better. And part of this is because I normally use black backgrounds. So let me go ahead and update that. Yes, that's what his original data looked like here. So you can see, that falling along one line, right? Now, what we could take from this, right, is we can fit this to an equation, it's linear. So it should fit to a linear equation where we have v being the velocity, h being some constant, and d being the distance. Okay, so v is velocity, d is distance, and h naught is a constant. And this is often referred to as Hubble's, or the Hubble constant. And based on the most up-to-date values as of July 2018 from the ESA Planck mission, this has a value of 67.66 plus or minus 0.42 kilometers per second per megaparsec. All right. And again, that was updated. Let's say that value is from July 2018 ESA Planck mission. And so if you're interested, you can look that up. All right. And so that gives us sort of this line. So essentially what this line tells us, if we just take a step back, is it says, based on the distance, based on how far away a galaxy is from us, there is a characteristic velocity associated with it. So the farther away that it is from us, the faster that it's moving away from us. The closer that it is to us, the um, the it's moving away from us less. All right. Now you might imagine, right, if this was a I don't if you would think about this in terms of if these galaxies sort of originated from maybe some sort of source and they were moving they have velocities based on that, you might expect instead that, say, our galaxy would not necessarily be at the center of this. Essentially, it wouldn't necessarily trend to the origin. The fact that it does tells us or gives us evidence that the universe is expanding because it falls on a straight line. That's the only way that this could reasonably be explained if you think about it, because otherwise, you would not expect it to trend back to the origin from any place that you sort of conduct this measurement. And so this gets at the expanding universe. And taking this one step further, we can get the characteristic time scale of the universe by 1 over Hubble's constant, right? And that gives us the approximate age of our universe. In actuality, we have to account for a few more things than just doing that calculation. So this characteristic timescale will be a little bit off. And so we have to account for relativity in an expanding universe. And this is often represented by a variable, or let's say a constant, f, such that the age of the universe is equal to f times 1 over Hubble's constant. And f is generally approximated as 0.96. All right. And part of this comes from the fact that the universe did not always, the ratio between energy and mass in the universe has and is changing. And so that's why we have to account for this f here. And if you go ahead and you were to calculate this out, you get the age of our universe, roughly 14 billion years old. All right. So now that we're able to get, roughly speaking, the age of our universe, and perhaps I'm going to increase the size of what you're seeing there to hopefully make that a little bit easier. Okay, so this now leads us to 14 billion years ago. And thinking back to that chart that we talked about earlier of the elements, we want to be able to explain that distribution of the elements. In order to do that, we have to start way back at the beginning, at the Big Bang. And so we're going to talk about nucleosynthesis, or the synthesis of elements, if you will, or nuclides, that started at the Big Bang. Okay. And let's say that at t equals 0, we have the Big Bang event. Okay. 100 seconds after the Big Bang, the temperature of the universe is roughly 10 to the 9 Kelvin. And there is a net formation of deuterium. And that's generally represented by 2 hydrogen. That's how you know deuterium, or D is the symbol. All right. And this hydrogen originated from the attraction of proton and electrons. And strong forces hold helium nuclei together. Okay. And for reference, strong force dominates within range of approximately 10 to the negative 15 meters. And so I jumped the gun on this a little bit because I haven't quite talked about helium yet. And so if we fast forward to, let's say, 30 minutes after the Big Bang, where we get lower temperatures for the universe. The universe at that time is about 10 to the 4th Kelvin. We have a universe that is 72% hydrogen and 28% for helium. All right. And these percentages are by mass. All right. And other nucleosynthetic reactions that could occur to get higher atomic number elements are inhibited due to Coulomb, if I can spell that correct, Coulomb repulsion. Yes. All right. And so what does that look like? So this is an image here of Coulomb repulsion here, the Coulomb barrier that one must overcome. And this is an attractive potential well, and this is due to the strong force, which I mentioned happens when it is a strong force, especially when you are very close together. All right, and it helps bind. Um, it helps bind protons and electrons and form these more stable atomic elements. All right. And the y-axis here is potential energy, and the x-axis is nucleon distance. So for this, we say, okay, well, we can't get this sort of strong force. We can't overcome this Coulomb barrier anymore because temperatures are much cooler now. So that this sort of makes sense. And we have a universe that's mostly hydrogen and helium, right? So that explains observation number one. Okay. And so the rest of the rest of the elements that are now synthesized in stars. So that takes us to stellar nucleosynthesis. And we're just going to go ahead and move that screen up. There we go. And let's say stellar nucleosynthesis occurs, say, for stars with masses of greater than and equal to about a little under 1/10 of the mass of our own sun. All right. And then we're going to distinguish that by sun with the capital S, right? So for stars with masses greater than 0.072, the mass of our sun, the star is hydrogen burning. Okay, and what does that mean? This means its core can sustain hydrogen fusion. We'll just make that a little bit prettier there. All right, and your reading covered some of this, but I wanted to just talk about the time scales a bit more than was talked about within the reading. So the first, so what does hydrogen burning look like? All right, and so this is, say, a proton-proton burning reaction here. And so if we have one hydrogen that is able to combine with another hydrogen, one hydrogen, that then is fused together to produce two hydrogen plus a positron plus a neutrino. And let me just correct this here. All right. Plus a neutrino and some excess energy, which I'm denoting here with the letter E. All right. And just for balancing sake, for the subsequent reactions we're going to do, I'm just going to show this as a set of two reactions. All right. And again, B is for positron, nu is for neutrino, and E is for energy. Now, for our sun, this time scale of this particular reaction is around 10 to the 9 years. So it takes 10 to the 9 years for one hydrogen to find another one hydrogen and be fused together. So it's waiting around for quite a long time. All right. And then once we have two hydrogen, we are able to take that and combine that with a one hydrogen. There we go. One hydrogen. And we are able to make helium. And that helium is going to be accompanied by gamma release and energy. And the time scale for this is about 1 second. So these timescales matter, and I should say these timescales are for our sun, right? So you can imagine if you maybe get more massive stars or less massive stars, these reaction rates can change, okay? And so then once we have this, we now have helium, right? And so what does that look like? So then helium, 3 helium can be merged with 3 helium. And again, we're doing a balancing reaction here. And so that multiplying this by 2, you notice both of these equations, gives us 2 helium, 3 here, okay? And then so we can take that helium 3, bring them together, and that forms 4 helium plus 2, 1 hydrogen, plus 2, well, would be 2 E, which is just what I'm using for energy here, all right? And then we would also be adding, excuse me, we'd also be adding gamma there, okay? And so now we have 4 helium. And that time scale for 4 helium coming together in our star would be roughly 10 to the 6th years. All right, so roughly 1 million years. And then this gives us, then we can do a net reaction here. And so the net reaction here is we started off with 4, 1 hydrogen, and we were able to produce 4 helium along with energy and other particles being released. And so that is hydrogen or proton-proton chain burning. Okay, so our star is fusing hydrogen. This doesn't get us yet to the bigger elements, right? And so we have to take into consideration that our sun is an evolved star. It was not one of the stars that, say, came earlier, right? And by evolved star, it's composed of elements synthesized by previous dead stars. Now, evolved stars primarily use the CNO cycle instead to synthesize helium. And so this means that while the proton-proton chain hydrogen burning is active within our sun, it's not the primary way that helium or hydrogen is fused in our star. But this gives us an example of what the earliest stars would have looked like. But because we have carbon, nitrogen, and oxygen as part of our stellar system and part of our star, there's a more efficient way that a star, particularly the size of our sun, prefers to fuse hydrogen. And so that is bringing together 12 carbon with 1 hydrogen, and that will create 13 nitrogen, and it will release gamma. And I should say this is a gamma ray here. We'll release a gamma ray plus energy. Now that 13 nitrogen is not stable, and so that will decay to 13 carbon plus a positron, a neutrino, and energy. And then we have our 13 carbon, and we use another hydrogen, one hydrogen here, and that yields 14 nitrogen, which is relatively more stable than 13 hydrogen. And then with that, we will also release gamma ray and energy. And then we'll have 14 nitrogen plus one hydrogen. And that will yield 15 oxygen plus a gamma ray and energy. Now, 15 oxygen in itself is not stable, so that will also want to decay into 15 nitrogen. And similar to the nitrogen decay, this will release a positron, a neutrino, and energy. Okay. And then for our last step here, we have 15 nitrogen, which will come together with one hydrogen. And that yields 12 carbon plus 12 carbon, plus 4 helium. So there's our helium there. Plus a gamma ray and energy. And so if we look at this net reaction, it too is similar to the proton-proton chain burning reaction. It is 4 hydrogen coming together to produce 4 helium, 2 positrons, gamma rays, and energy, and neutrinos, right? And so this one, again, is the CNO cycle. Okay. And as you see, we started off with 12 carbon, and we ended up with 12 carbon, which is why there is no carbon in the net process. All right. And the key of this cycle is that it is catalyzed by carbon, nitrogen, and oxygen. Now, both the proton, I'm going to note proton-proton chain burning, and the CNO cycle, which perhaps just for reference, I will make this into a similar heading as that. So both the proton-proton chain and the CNO cycle need temperatures greater than 10 to the 7 kelvins to proceed. All right. And this is what helps us determine earlier sort of that mass for a star that can actually fuse hydrogen. All right. Now, a star will shrink when hydrogen fusion ends. Now, for stars that are sufficiently massive, when T reaches roughly 100 million Kelvin, helium fusion can begin. And so, page down here. This is often done in what's referred to as the triple alpha process. I will denote that there. New section heading. And we'll just correct this to make it look like one single font. All right. And this happens in stars. This occurs in stars that have a mass of 80% of our sun. All right. They are able to go through this helium burning process. Okay. And this is often known as, you might be familiar with this, I should say, red giant stage, right? So you've probably heard at some point that our star, the sun, will go into a red giant phase way beyond our lifetimes. And that's the point at which it starts fusing helium. So, relatively speaking, this process is relatively straightforward. In that last process, we produce four heliums, right? In both of those chains. So we have four helium that can come together with four helium and form eight beryllium. And this, now the half-life, I should know, half-life for a beryllium in this instance is 10 to the negative 16 seconds. All right. So this is a very, very fast process. Okay. And the reason that is because 8 beryllium is not around for long enough. It quickly finds a 4 helium, which goes straight to 12 carbon. Right? So understanding this tells us why. So the short half-life of 8 beryllium explains why you need high temperatures and pressure. It also skips lithium and boron, which explains observation number 4, all right, that we noted earlier, right? That lithium, beryllium, and boron are anomalously rare because they are not created through this stellar nucleosynthesis process, all right? And we're going to go ahead and bold that. Now, the other thing that we can say from this is carbon is the first stable element made beyond hydrogen and helium. And let's correct. All right. So beryllium has a very short half-life, so it doesn't want to, it's not going to stick around. Or beryllium 8 beryllium, so it would decay, right? And so with under high temperatures and pressures, you can find this 4 helium quickly and start to get to a more stable element. All right. Now, just fast forward a bit. So when you get higher in temperature and pressure, you can get more helium addition occurring, right? And so this is through maybe a more general alpha process. And so in this, you get 12 carbon, for example, right? That finds a 4 helium, and then can make 16 oxygen. Then you have 16 oxygen, which can go forward and create with a 4 helium to create neon. And then you can have 20 neon combining with the 4 helium, right? And so I think you all get the idea here. And this process can just keep occurring, right, with the addition of 4 helium. Now, one of the issues that you run into is that this becomes increasingly difficult due to increasing Coulomb repulsion with increasing Z. Right? It becomes harder and harder to have enough energy to sort of bring these elements together. And so this explains observation number 2. And if you recall, observation number 2 was that elemental abundances generally drop with increasing atomic number. Okay? And this process, this alpha process, continues all the way up to, and you might be able to guess this based if you refer back to the chart that we looked at earlier of elemental abundances. But this continues up to 56 nickel. Okay, which then goes to 56 cobalt, which goes to 56 iron, right? So again, let's go back to our PowerPoint that we had earlier, and let's take a look. So if we go back to this PowerPoint here, quickly run through. So here is 56 iron, and so it can produce all the way up to nickel, right? 56 nickel, but it's not stable, so it decays down to iron, 56 iron. So this is sort of the last stable product of this process. And this explains why this is anomalously, why 56 iron is anomalously abundant. Okay, so let's go ahead and note that. Excuse me. And so this explains observation number 5. All right. And so this process of helium addition also explains, and we're going to spell that correctly. The process of helium addition also explains observation number 3. Right? Even Z element preference that occurs because we're adding helium-4, right? But ultimately, this favorability in general for even atomic numbers is determined by quantum mechanical laws. All right. Now, this also partly, I would say, explains observation number 6. Right? And this is that TCPM have odd atomic numbers. Okay? Though I'd probably say ultimately, and we're going to, ultimately, this one is due to the fact that they have no stable isotopes. So they're just not stable. All right. And so other elements beyond 56 iron are not produced, or I would say are not stably produced through nucleosynthesis. And there are some caveats there. Okay. And so one of the reasons that explains this is that if we take a look at this is a chart of the average binding energy per nucleon versus the number of nucleons. So we have iron 56 here, and you can see hydrogen, helium, carbon, oxygen, whatnot here. And so what you can see here is that you get that energy is released essentially all the way up into iron 56, and then this starts to go down, right? And so that's telling us that for heavier elements like uranium, they release energy through decay or fission, right? It kind of makes sense considering um, what we know about uranium. And so, one question that you might have is, well, okay, well, say that these want to decay. How do we get them in the first place? And I mentioned that earlier that there's not this stable process that generally occurs for a lot of these, like we've seen for sort of this alpha process. Because once you go beyond iron 56, there is a decay process that wants to happen. But for really big stars, and particularly very early in the universe, some of these uh, elements that have very, very short half-lives were able to combine, and eventually there are stable elements that exist far enough up. And this was covered a bit in the reading. And so you could quickly merge a bunch of unstable nuclides to get to a stable form. And then through decay processes, you can decay to stable elements. All right. And so this is generally how we get elements beyond iron 56. And if you're interested in learning more about this and reading more about it, you can not only consult your reading, you can also consult Principles of Organic Chemistry, as well as General Planetary Science book by DePotter and Lasar, chapter 12. And let's go on to the next slide. So I want to supplement your reading and look at aspects of stellar formation that I would like to elaborate on. So when we think about the formation of any stellar system, or particularly our solar system, it's generally divided into a set of phases. And so I detail and list those phases here. If you find another set of readings, sometimes those phases differ. But the general process is as follows. You start with a molecular cloud, or perhaps a giant molecular cloud, which then fragments into a single molecular cloud. And then we follow the evolution of that molecular cloud through collapse. Once that molecular cloud starts to collapse, at the center of that molecular cloud, a protostellar object begins to form. That protostellar object is what eventually becomes the star for that system, in our case, the sun. Then that protostellar object begins to go through its evolution, in which material might outflow from it. And then it'll go through a T-Tauri phase, which is named after a particular star that we see, a named star. And then material surrounding that star begins to disperse, and you're left with a stellar system. Now, there are certainly some gaps here that I didn't fill in through this, but this is the process that gives us our everything that we see in the solar system in the arrangement that we see it and explains those observations on the last slide. Now, the part that I would really like to focus on here is that of the molecular cloud and molecular cloud collapse. So first, then, we should start off with the definition of a molecular cloud. So a molecular cloud is a cold, dense object that it's mostly comprised of hydrogen and helium. And these objects are not dense at all. We're talking a few thousand molecules per centimeter cubed. And their mass can range, say, for example, anywhere from one solar mass up to a million solar masses and even more. All right. So this is just typical, I would say maybe a typical range for based on observations. And the nominal temperatures for these molecular clouds are somewhere between 10 to 30 Kelvin, so pretty cold. Now, some of the examples of these molecular clouds that we see on the smaller side are known as Bok globules. These have around 10 to 50 solar masses, and these are sort of these dense clustered pockets of mass here. But then you can get up to some really, really massive molecular clouds. An example of that is Sagittarius B2, which has 3 times 10 to the ninth solar masses of material. So the size of these molecular cloud the sizes of these molecular clouds can really vary. And in the case of Bok globules, you're generally maybe talking about an object that could be as little as a light year across. But then you can go up to objects like Sagittarius B2 and you're measuring this in hundreds of light years on that sort of scale. So we're talking about these, not only these really massive objects, but these very, very big size-wise objects. So then it begs the question, how do we get them to a much smaller scale on the scale to where we can compact that material and form it into a stellar system? And a lot of our information comes from what we observe today. So typically, an interstellar cloud must be somewhat stable against collapse, right? Or we probably wouldn't observe them still. And so, with all this mass, one of the questions that we can ask is why hasn't a given molecular cloud, collapsed under their own gravity? And there are a variety of reasons for this. One is that gravity alone is not sort of the predominant force that operates in molecular clouds. So, and we know this because if it was, they should all collapse. So, some of the other forces that are present are there is a net angular momentum to a cloud, right, which can impede collapse. There is a gas pressure, right, which wants to push outwards. And there's also magnetism, right? And so all these act to prevent, for example, cloud collapse. But we know if we postulate, right, if we're saying that these molecular clouds lead to stellar systems, we know that there are situations in which they do collapse. So under what conditions do these collapse? So if we were to assume that a molecular cloud, the energy of that molecular cloud is thermal, then we could look at and use what's referred to as the virial theorem, which essentially states that for a cloud to collapse under its own self-gravity, um, it must have twice the amount of energy in its gravitational potential energy, that is, as it does in kinetic energy. And for kinetic energy, we're thinking in terms of, say, gas pressure or thermal energy. So, again, to restate that, the gravitational energy, the gravitational potential energy of a cloud must be greater than twice the kinetic energy. Okay? And so let's switch over to our chalkboard and look at some equations. Okay, so we're back to our notes here, and we're just going to make this bigger. And what we want to explore is under what conditions do molecular clouds collapse? And I noted earlier that we can use the virial theorem, which says that if which says that for a molecular cloud to collapse under its self-gravity, its own gravity, the following must hold through the collapse process. Right? And again, that's that its gravitational potential energy, and I'll make this a little bigger for you. Its gravitational potential energy, or its magnitude of its gravitational potential energy, is more than twice that of its sort of gas pressure or thermal energy. Okay, so we can dive into this a little bit further. All right. If this is true for a molecular cloud to collapse, again, when we're assuming that all of its energy, and I'll note that here, I think it might have been noted on the slide, but the assumption here is that molecular cloud internal energy is thermal or gas pressure, okay? Which is a reasonable assumption for a molecular cloud at very low temperatures. So, if this is true, right, which it is, um, we should also then be able to infer that for cloud collapse to not only initiate, but for it to also be sustained, this condition must be met. And so, if we say we took some time, and let's say that this is at time, let's say T1, we know that this condition, if we want this cloud to collapse, must be met. And then we're going to rearrange that equation a little bit. This is directly from this theorem here, the virial theorem. And all that I did here is I went through and I divided both sides by 2. And because gravitational potential energy can be represented as negative, another way of thinking about this is in terms of conservation of energy. We know that the energy of a system, while it might be partitioned into different forms, should remain unchanged unless that system is doing work. And so let's think of kinetic energy in traditional terms as, say, maybe velocity, right? And if we think of the planet Earth and we think of a mass that's approaching planet Earth, that mass, when it gets closer and closer to Earth, Earth's gravity is going to speed that up, right? And so the kinetic energy, the traditional kinetic energy, which is 1/2 mv squared, will increase, right? But we know that the total energy of that system must be conserved. So that must mean there's another energy term that decreases, right? And for potential energy, particularly gravitational potential energy, which is represented as a negative, or when you get closer to, say, Earth in that example, the potential energy, the magnitude of the potential energy increases, but it's negative. So it actually, when you're thinking about it, it actually decreases. And so it balances that out. Okay. And so in this instance, gravitational potential energy, we use that same thought process here where gravitational potential energy is treated as a negative. So all that I'm doing here is essentially removing those magnitude brackets here and sort of propagating the negative that tends to be associated with the gravitational potential energy. Okay. And so again, at time t1, again, we can think if we want to think about this in terms of magnitude, we're just rearranging this equation. The magnitude of the gravitational potential energy, again, magnitude is when we put those bars on the side and we take the absolute value. One half of the magnitude of the gravitational potential energy is greater than the kinetic energy of the system at time t equals 1. Now we can do the same thing. We can copy the same equation, right, for time t equals 2. Sometime later, if we expect that molecular cloud to collapse, this must still hold. And we'll make sure that's t sub 2 there. And then we can combine these equations, right? And through combining these equations, what this tells us is that and I'm just for a moment, I'm going to go back to sort of this magnitude notation, just for simplicity, that the magnitude of the gravitational potential at time 2 is greater than or equal to, and let me correct that, it's greater than or equal to that at time t1. That follows from this equation when t2 happens after t1, right? So we could modify this and say at time t2, right, where t2 is greater than t1, right? And then this holds. I'm going to click and remove the page break here since we don't need that for this. And so we know that the gravitational potential energy at time 2 must be equal to the gravitational potential, greater than or equal to the gravitational potential energy at time t equals 1. So that means, and another way of thinking about this, we can rewrite this equation, or we can use this to sort of move forward in thinking about these two equations. And so if we, for example, let's subtract time t2 from t1, all right? And if we do that, we get the following equation, which is 1/2 of the difference between the two is greater than the difference between the kinetic energy. And so let's go ahead and rewrite this equation here, or reduce it. And we're going to do that by taking for each g term the time step at t2 less that at time step of t1. And we're going to subtract that and call that delta, the delta for the energy term. So for this side, the potential gravitational energy at t2 less t1 is delta, the gravitational potential energy. And we can do the same thing for this side, which has the kinetic energy. And because there's a negative sign in front of both of those terms, we just propagate that through. And so now let's take a step back for a moment and think in terms of conservation of energy. So as this molecular cloud is collapsing, right, this constraint must be met here. And that constraint is only met when this equality is satisfied. Now, we can also think about conservation of energy. Conservation of energy means that we have this system which has a given energy, and if that system is not doing work elsewhere, the energy of that system should be conserved. So in this particular instance, as you take all of that mass that was well distributed and you begin to collapse it down and down, the gravitational potential energy should decrease, right? Or essentially get more negative. And what this is saying is no more than half of that gravitational energy, no more than half, can go into kinetic energy, which is a problem for conservation of energy, right? Because that alone does not allow conservation of energy. Okay? If no more than half of the gravitational energy can go into the kinetic energy, then this would tell you, this would suggest if you have no way to get rid of that excess energy, this would then say, well, there's no way that cloud collapse should be able to continue. So let's just write that down. That no more, this inequality tells us is that no more than half of the lost gravitational energy can be converted to kinetic energy. So what does this mean for the total energy? So if we come up with an equivalent change in the total energy of the system, which I'm going to denote by delta E with total as the subscript there, that tells us that the change in energy for the system, just note it here, is equal to the change in gravitational potential energy plus the change in the kinetic energy of the system, right? And we have already established that the kinetic energy can be no more than half that of the gravitational energy. So let's go ahead and, let's make that substitution. Let's say that we'll just propagate this through here. So we'll continue. We'll keep that delta gravitational potential energy term. And for the kinetic energy, let's say that, it's at its maximum and that it can take half of the gravitational potential energy. All right, we get that. And so what that is telling us here is that we have a big term, a big chunk of energy here that is not accounted for. Okay, and just for reference, I also want you to know that this term here actually comes out to be negative, right? And again, it's because of what I earlier explained, how we deal with and how the sort of signage that we generally use for potential energy. All right, gravitational potential energy, excuse me. And so where does that energy go? All right, well, what this is telling us is we know, because we were representing kinetic energy for the energy of that system, which is in gas pressure, this is telling us that at least half of the gravitational energy change must be lost from the system. So take a minute and think about that. And think, how might a stellar system lose energy? All right, now that I gave you a moment to think about it. Well, essentially, what this predicts is that forming stellar systems should radiate, right? That your heat, as it collapses, material is going to heat up, and you should be able to radiate that out. And if it's radiating, it should be detectable, right? We should see it, which is true. We do. We see evidence of this. So as that molecular cloud collapses, there's a big portion of that stage where it's radiating out lots of energy. Okay. Now let's go ahead and go back to our slideshow. All right, we're back at the slideshow. And I'm just going to make it a little bit smaller there. There we go. And that moves us to the second point here from where we left this presentation. Gravitational potential energy is converted into thermal energy. Now, early on during this collapse process, the cloud is optically thin and it can radiate heat away, right? We're talking about a cloud that is, started off few thousand cubic centimeters of material density. And mostly it's also, and I should also say, it's transparent to infrared wavelengths, right? Really allowing it to radiate. Now, as this cloud collapse continues and continues, eventually it'll become optically dark. But what it's telling you is for a large portion of that collapse, where you still have that cloud, the core can stay cool. And while that heat is radiated away, relatively cool. All right, let's go ahead and move to the next slide. So as we start to collapse, we get collision of grains and gas in the cloud, and then that cloud begins to fragment. And that helps, as you get all these sort of interactions, it helps to equalize the direction of all the gases and all the materials in that cloud. And then the cloud fragment gets an overall sense of rotation. Not to mention, if you go out to something that is very large, right? Let's see where my hand is here. There we go. Very large, and we go to very small. If you think about conservation of angular momentum, right? I can have something that's, say, very far out, and maybe there's a net angular momentum, but it's really small. It's not like things are whipping by really fast. But when I collapse that in, right, it's going to rotate, right, at velocities that are much larger at what it was doing when it was sort of out here, okay? And that's from the conservation of angular momentum. So these collisions and this collapse process helps give it an overall sense of rotation. So there's an outward pressure in all directions. And what also happens is to help equalize as these gases are passing by each other. Remember, we have this big cloud. What happens is gases that are above and below, or material that's above and below this sort of ecliptic plane, it's actually going to want to move downward due to all these interactions. So it's going to collapse down to a disk. And if you think about our solar system and everything essentially being along the ecliptic plane, this is an explanation of that. And also that net sense of rotation also explains why, generally speaking, the planets rotate in the same direction and why they orbit the sun in the same direction. All right, let's move on to the next slide. So gravitational collapse continues, and I don't think this image is going to show up as clearly, but as gravitational collapse continues, the core of this molecular cloud gets really, really dense, and thermal energy cannot escape. All right. And this pressure increases and the temperature increases. And then within the core, you get H2 dissociation. Okay. Now, this molecular cloud core then transitions into a protostars. Again, protostars do not have ongoing fusion. And then I mentioned that dust settles to the midplane, creating an accretion disk. I sort of mentioned this earlier. Okay. And there's also bipolar outflows from, excuse me, from the stellar, the protostellar or the protostar. And part of this comes from you can this protostar is accreting lots, it was accreting lots and lots and lots of material. And there comes a point into which that the amount of accretion once you get this hydrostatic equilibrium being reached and you still get this massive inflow, it wants to eject some of that material away, right? And so the way that it does that is through sort of flow, bipolar flow that's oriented perpendicular to the orientation of the accretion disk. All right. And so the general stage, we start off with this molecular cloud. We get gravitational collapse. We have protostar formation. We move into this Tari phase, right, where we now have this cloud envelope now goes away. It's been dissipated. And we still have outbursts that coming in from the star because the star there's still this accretion going on for the star. Eventually, the star stops accreting and you're left with a debris disk. That debris disk begins to allow accretion, and planetary bodies begin to accrete and form. And then eventually we get to a star system. All right. And the timescales here are indicated as well as the distance. So getting up to a protostar from the time of gravitational collapse takes up to 100,000 years. Go back here. And then it can take up to 3 million years before we get to sort of this protoplanetary disk and sort of this removal of this envelope surrounding the protostar. I don't know why that keeps going forward. And then within a period of, say, 50 million years, we go from this pre-main sequence star, and that's into the sort of central star that is on the main sequence, and where we have planets and the debris essentially is gone and planets have accreted. And for the final part of the lecture, I just want to conclude that a reason that we have a great understanding of how stellar systems form, how stars form, is by looking at other systems that we can observe in the night sky and through telescopes. So there are a few stars that have names, Sirius and Mira. Mira is a red giant, and Sirius is the brightest star in the sky. It's about 9 light years away from Earth. Now, most stars are cataloged by type. And what we see and from stars, from making a number of observations, is we find that when stars are fusing hydrogen, they are on what's termed the main sequence, which is along this diagonal here. And once they stop fusing hydrogen or before they're fusing hydrogen, they'll bounce a bit over sort of this. So I believe our sun, when it goes red giant, it'll maybe head over here in this area. And the lifetime of a star sort of fusing hydrogen will depend on its size. So what you'll see is that a star that's, say, 60 times the mass of our sun is higher up in luminosity and in temperature. So this is to the left is increasing temperature here, to the right is decreasing temperature, and luminosity or brightness on a log scale is shown on the y-axis. And then lastly, observe disk. We see disk. We see those where we can see the central protostellar object and those in which we can't. And by looking at lots of different disks at various points in its evolution, and particularly as clouds collapse and they're radiating this energy, we can observe that. And so that gives us great observations and insight into how our stellar system formed. Now, this can be paired with cosmochemistry and understanding of the ages of material within our solar system to then go back and get the age at when certain events happen within our local neighborhood. Okay, so this concludes our lecture. And if you have any questions, you can always email me or the TA for the course, Evan. And I hope to see you all Thursday.